Hello everyone. In the last lecture, we have learned about the fundamental theory of static analysis called abstract interpretation. The theory provides the guidelines about how to design a correct static analysis that soundly subsume all possible behaviors of a given program. Okay. In this lecture, we are going to design a sound static analysis from scratch and prove its soundness, and finally learn an efficient algorithm to compute the abstract semantics. Okay, let's get started. Let's design a sound static analysis of SmaLLVM following the abstract interpretation framework. Here is the roadmap. So we will design concrete semantics of a program as a set of reachable states, as we discussed in the last lecture. And then we are going to abstract the set of states as a single abstract memory per each program label. Okay. In concrete semantics, there can be infinitely many reachable memories at a program label, but we will abstract them into a single abstract memory using the interval domain. And because the abstract domain has infinite height, so we have to design a widening and narrowing operator. So let's review the SmaLLVM language. So a program consists of a set of program labels and the control flow relation called next. Okay. And then each program label is associated with a command denoted by cmd over L, like this. Here is the definition of the syntax that you are already familiar with. First, the standard semantics of the SmaLLVM language is the same as before. Okay, but in this lecture, for simplicity, we interchangeably use Boolean values here as integers 0 and 1 in the standard way. Okay, here is the semantic domains, the same thing as before. Next, we define the transition relation between two states. Okay, the semantics is defined by a transition system, which is actually the same as before, but I just simplify the definitions and give explicit names for each semantic operators, like update here, eval or filter, and so on. Okay, fundamentally it is the same definition in the previous lecture. So here we define the semantic operators. So first, memory update function that takes a value, okay, here, and a memory here, and return the updated memory like this for the corresponding entry. And next, expression evaluation operator eval here, okay, that takes a memory and returns the computed value according to the expression, okay, and given memory. And the memory filter operation will determine transitions at conditional branches. Okay, if the expression, this expression, is evaluated to true under a given memory here, okay, then the output memory is defined as the same memory, which is the same as the input memory. Okay. Otherwise, which means that if this expression is evaluated to be false, then the output memory is not defined. Okay, which means that there's no transition. Okay. Sometimes we interchangeably use this one instead of true. Okay. Now we are ready to define the concrete semantics. So before getting into the details, let me informally show you how the concrete semantics looks like. So let's take a look at this simple example. A simple SmaLLVM program with a loop. Okay, it takes an input from the user and iterates the loop depending on the input value. Then what is the set of all reachable states of this program? So let's see each trace depending on a given input. Okay, for example, for input 10, right, the trace looks like this. initially at label 0, which means before executing the command at 0, okay, the memory is empty, which means no variable is defined. After one step at label 1, variable x will have the input value 10, okay, and then it will skip the loop because of the condition and finally reach this point, label 3, okay, with this memory. How about input 9? Okay, this case. So initially it starts from the input, the empty input memory as before. It reads value 9 at label 1. And because here 9 is less than 10, it gets into the loop, okay. And then it increases the value of x by 1, okay. And then because of the condition, it exits the loop, okay. If we consider all possible input values like this, okay, there are infinitely many traces. So the concrete semantics of this program, which is defined as a set of all reachable states, is defined as follows. Okay, for each trace, we ignore all the history of the trace, and we just collect all reachable states. Okay, and the final result is the union of, okay, all such reachable set of memory states. Okay, this is a definitely infinite set, so it is uncomputable, right? So we need abstraction. Then next, let's formally define the concrete semantics and concrete domain. Okay, the concrete domain D is defined as the power set of states. Okay, each state is pair of label and memory. Okay, so this mathematical space, this space, represent our intention well. Next, we define the concrete semantic function. Okay, this has the following type. A given set of states, it will produce a next set of states, okay, that describes the super transition as we discussed in the last lecture. Okay, here this I is the set of initial states, okay, and the function step, this function step is just a PowerShell lifted version of the transition relations between two states. Okay, this is defined as follows. Okay, for each state, right, for each state S in the input set of states, we apply the transition relation and get the output and collect all such outputs. Okay, that is the output set of states. Okay, this function represents our intuition perfectly. Okay, then how to describe the concrete semantics, that is the reachable set of states from the initial state. So as you may guess, fixed point is a good mathematical tool to describe such an inductively defined mathematical object. Okay, starting from the initial state, you continuously collect all reachable states, okay, until you reach the fixed point. Then the fixed point is all possible reachable states. Okay. So before starting the actual formalization, let me introduce some notations we will use in this lecture. So an element of this function space is interchangeably an element in this space. Okay, it is actually trivial because function is just a special case of relation, right? So we will sometimes interpret a function of this type as a relation in this type. Okay, and how about the reverse? Okay, if we have a relation of this type, okay, then what is its function version, right? because there can be multiple images of a domain element, right, which is not allowed in function space. Right? So we interpret the relation as a function in this space, okay, instead of this space. Okay? For example, a transition relation between states, right, as we defined, can be interpreted as this function with this type. Okay, it means that it takes an input state and return all possible set of next state. Okay, and then we will use this notation, which is a PowerShell lifted version of a function, okay, whose type will be like this, and it will compute this set. Okay, next, suppose we have a function with this type. Okay, then we will use this notation as a shorthand for this one. What does that mean? That means for each element x, right, in the input set, we apply this function f to x. Okay, then what is the outcome of this f? That will be a set of element of b, right? And then finally we merge all the sets by union to make a big set. Okay, that is the definition of this expression. Okay, with this notation we can simply rewrite the step function with this type. Okay, first we consider the transition relation here as a function of this type, as we discussed in the last slide. Okay, and then the step function can be simplified like this. It means that given a set of input states, we apply this transition function for each element in the input set, and then we collect all of them to make an outcome, right? Then we can simplify this definition into this one. Okay, that is actually semantically the same as the original definition. Okay, and then we will use this notation, pair notation, to make function pairs using two functions. Definition is as follows. Okay. Then so far we have designed the concrete semantics, and now we understand how the concrete transition works conceptually. And let me show you how the abstract transition works and how the abstract semantics is computed. Let's take a look at this same example. So here our goal is not to collect all the reachable concrete states, but we want to compute an abstract memory for each label. Okay, so the abstract domain D# will be like this. So this is a mapping from labels to abstract memories, right? So that means for each label we will compute a single abstract memory that subsumes all reachable concrete memories at that label. Okay, and suppose we have a single abstract memory per each label at some point during the analysis. Okay, for each label we will pick the input memory here, and then we will apply abstract version of the transition relation. Okay, here as you can see, after applying the abstract transition relation, we will get this output. So for some commands like assignment or input like this, okay, the outcome will be a single abstract memory for the immediate successor. Okay, but for some other cases like conditional branches like this, okay, in that case the outcome might be multiple abstract memories, right? Because the input is an abstraction of multiple concrete memories, right? Such that some of them satisfy the condition, right? But the others may not satisfy the condition. Okay, so in general, the abstract memory can be split into two parts after this conditional branch. One for the true branch, which is label 2 in this case, and the other one for the false branch, which is label 3 in this case. Okay, so the next step is to partition the newly generated memories, this set of red cells, okay, and send them to their correct destination. Okay, this step is called partitioning. So as you can see, now for each label, right, there is a set of abstract memories that are generated from the previous iteration. Okay, after partitioning, each abstract memory goes to the right destination. Okay, but as you remember, we want to keep a single abstract memory here per label. Okay, so we will merge them by joining multiple abstract memories at the same label. Okay, then finally we obtain a new mapping from labels to abstract memories like this. Okay, so that is a single step of static analysis. This static analysis will perform this step continuously until reaching fixed point. Okay.